Now, the intersection of two left or right ideal in a ring R is again a left or a right ideal. So, for example, if A and B are left ideal of R, then we need to show that A intersection B also is a left ideal of R. So, for this one, you take let A and B belong to A intersection B. So, A belong to A and A also belong to B. Similarly, B belong to their intersection. It implies that B belong to A and B belong to B. Now, A belong to A and A belong to B, or A belong to A and B belong to A, it implies that A minus B also belong to A. This is by that necessary and sufficient condition of an ideal. So this implies that A minus B belong to A. Similarly, A belong to B and B belong to B, it implies that A minus B belong to B. Since A and B are ideals of R. So now, next let R belong to R and take A to be an element of A. Then this implies that RA also belong to A. Why this is possible? Because A is a left ideal. Similarly, A belong to B. So, and R belong to R, it implies that RB also belongs to B, since B is a left ideal. So now what we have is that A minus B belong to A minus B belong to B. It implies that A minus B belong to their intersection, A intersection B. RA belong to A and RB belong to B. It implies that RA, here I am taking this one because A is also an element of B, so RA belong to B. So RA also belong to A intersection B. Similarly, RB also belong to A intersection B. So by that necessary and sufficient condition for S to be a subring of R, we can conclude that A intersection B is also a left ideal if both A and B are left ideal. Now, how we define the ideal generated by a subset of a ring R? So take R to be a ring and S a subset of R. So if you take set II which contained S a subset of R, then J is equal to intersection of this II will be the smallest I will be the where I suffix I are ideals. These are ideals which contains the set S. Now this G which is the intersection of all these ideals, I suffix I where I belongs to set of natural numbers only. So this will also be an ideal by this previous theorem. But the intersection also will contain S, because each of this ideal, say I1, I2, I3 and so on, this contain S. So their intersection also contained S, and therefore in this case J is called the ideal generated by a subset of a ring R. So that is the definition of ideal generated by a subset of a ring. Now let me define you the definition of left ideal. The principal left ideal. A left ideal generated by a singleton element A, and it is of the form SA such that S belongs to S. So this ideal is called as the principal left ideal and it is denoted by RA. Similarly, the principal right ideal is denoted by this one. If it is generated by a singleton element, that means every element of that ideal will be a multiple of A. Here also, but multiple of A from the right side. So therefore, for this one principal right ideal, we denote it by AR. So now here, the remark of this one is that if one belongs to R, then set RA such that R belong to R. This one is a principal left ideal of R. Similarly, AR will such that R belong to R. This is a principal right ideal. Now, the ideal generated by 1, that means the ideal generated by 1 will be will be denoted by S is equal to R into 1. So this one is equal to R itself. So if it is the ideal generated by 1, then in that case it will be the whole ring itself, and the ideal generated by 0 by a singleton element, by this element 0, then it will be equal to R into 0, which is equal to 0 itself. So it will be a 0 ring. Now this ring R and 0, this ideal R and 0 are called the improper ideals of R. Other ideals other than this one, R and 0, will be called as the proper ideals. Now a ring R is called a principal ideal ring. Before we come to the principal ideal, then here principal ideal, that means if it is ideal generated by a singleton element A, and if it is both left and right, that means if that ideal generated by a singleton element A is both a left ideal and a right ideal, then in that case it will be called as the principal ideal. Now a ring R and a plus and dot. Okay, consider a ring R. Let us take this one. Then if every ideal of R is a principal ideal, then in that case this R plus dot is called as the principal ideal, it is called as the principal ideal ring, since all the ideals of R are principal ideals. Now for example, this one, you'll see that 2 set or 3 set and the plus and dot, this one is a principal ideal of set plus and dot, because this 3 set plus and dot, it is the ideal generated by 3. It can be written as set into 3, or which is same thing as 3 into set. So therefore this 3 set and the plus and dot is a principal ideal of set and the plus and dot. Not every ideal will be a principal ideal, so you have to note down that one. Now next one is that a fill will have no proper ideals. That means the only ideals of a fill will be the whole ring itself and 0 ring. For example, now here you take, let A be a non-zero, or we can take, let S be a non-zero ideal of F. So what I need to show is that this S will be equal to F exactly. So if S is a non-zero ideal of F, then that means that S will contain at least one non-zero element. So S contained at least one non-zero element, say A, where this A is not equal to 0. Now A belong to S will imply that A belong to F also, because S is a subset of F. And since F is a fill and A is a non-zero element, it implies that A inverse also belong to F. Now A belong to S, A inverse belong to F will implies that A into A inverse will belong to S. Why this is possible? Because S is an ideal of F. That is, the product of an element in S and an element in F must be in S, since we assume that S is an ideal of F. So this implies that what is A into A inverse? It gives you 1. So that means 1 belong to S. So now for every X belongs to F, it will implies that X into 1, which is equal to X, this also belongs to S, because S is an ideal. So if you multiply an element of S, that is 1, with an element of X, so it will be in S only. So X also belongs to S. But we know that from here you see that every element of F is also an element of S. So which means that F is a subset of S. But since S is an ideal of F, so first of all S should be a subset of F. So we have that S is a subset of F. So from this one and this one, we can conclude that S is equal to F. That means if there exists a non-zero ideal of F in a fill F, then that non-zero ideal must be the whole fill itself. It is equal to F. So that means a fill will have only will have no proper ideals. It will have only the improper ideals, the fill F itself and the zero ideal. Now the last one is this one. A commutative ring with unity is a fill if it has no proper ideals. Now we know that a commutative ring with unity need not be a fill. For example, this one, set under plus and dot, this one is commutative and it has a multiplicative identity 1. But it is not a fill because, for example, 2 belongs to set. The inverse of 2, 2 inverse is called 1 by 2, which does not belong to set. That means it is not a fill because every non-zero element of set has no inverse in set. But now if it has no proper ideals, then in that case, a commutative ring with unity is a fill. So let us take this one. So since let us take A to be a non-zero of R. So if A is a non-zero element of R, then we know that RA, which contain the elements R into A such that R belong to R, this one is an ideal of R. And this ideal RA contained one non-zero, at least one non-zero element, and that is A itself, because we assume that A is a non-zero element. Now, since 1 belongs, because here it's given that it is a ring which commutative ring with unity, so that means 1 belongs to R. So 1 belongs to R and A also is an element of RA. So in this case it implies that since 1 into A is equal to A, this belongs to RA. So now it means that RA will be equal to the whole ring itself, because it's given here that that ring has no proper ideals. So if RA is a non-zero ideal of that ring, commutative ring with unity, then it must be equal to R itself. And now RA is equal to R will implies that their axis B belong to R such that B into A from the left side, because RA is equal to R, so that means there exists an element B say in R such that B into A is equal to, because 1 is an element of R, so it is equal to 1, which means that this non-zero element A has an inverse B in R. So this implies that every non-zero element in a ring every non-zero element in a ring which is commutative with unity and has no proper ideal has an inverse in R itself. So this implies that a commutative ring with unity is a fill, because every non-zero element here has an inverse, because I'm taking A to be just an arbitrary non-zero element. So it will be true for any other non-zero element of R. So from here we can conclude now that a ring which is commutative and has multiplicative unity and also has no proper ideals other than F itself or other than the ring itself and the zero ideal, then it will be a fill. So this shows that a ring which is commutative and has multiplicative identity 1 will be a fill if this condition is satisfied. It has no zero ideal, because here the ideal RA cannot be the zero ideal because it contained a non-zero element A. So the only option for this RA is that it should be the whole ring itself, because R has no proper ideals. And if it is equal to R, then you can see from here that RA is equal to R, and RA is equal to R implies that we know that 1 belongs to R. So there must exist an element B belongs to R such that B into A will be equal to that element 1 in R, which means that B is the inverse of A, and this implies that the non-zero element A has an inverse in R. So since A is an arbitrary element, by taking any other non-zero element, say X, Rx, you can form Rx, and you can show that X also has an inverse in R. So from here we conclude that a commutative ring with unity is a fill if it has no proper ideals. This question was asked in 2002, then 2013 also. So you go through again this thing. If it is clear, then it's okay. Otherwise, you please tell me what are the steps that are not clear to you.